So welcome to the technical advantages of deploying Fronius as your commercial solution. Today, your superstar host will be Timmy. He's one of our technical advisors in the application engineer team, and myself, Matthew Bolsnak.
Hi, guys.
So what we're going to be covering today is the SolarNet and the Snap-in inverter series benefits. So we're going to be touching on some overdimensioning capabilities, getting to know the Fronius eco, the ins and outs of it, the system design, some communications associated with that, and then really digging into centralized and decentralized systems in relation to the Fronius eco. We're going to be touching on some of the project comparisons that we've created with those particular sorts of sites. Some secondary protection integration that you may not have thought about in the past that could potentially save you some time and money on some of those sites. The smart meters that are going to be integrated into these particular sites, so mainly the two larger commercial smart meters, which is the 50 kA and the 480 VUL, sorry. And an interesting topic that's coming up a little bit more in Australia these days is the PV-Genset side of things. So let's have a look at the SolarNet and Snapchat series benefits firstly. So in terms of over-dimensioning capabilities, now bear in mind that yes, there are actual specific over-dimensioning capabilities for STC systems under CEC regulations. However, in this particular case, the two main inverters that you're going to be using on commercial sites are going to be either the Fronius SIMO, which is anywhere between 10 to 20 kilowatt AC nominal output. These particular inverters can be over-dimensioned by up to 150%. So meaning that you can actually have a look at being able to utilize that additional capacity in an LGC sort of scenario. On the other side, we've then got the eco, which is comes in a 25 or a 27 kilowatt. Both of those can be actually oversized DC to AC up to 37.8. Now, in terms of the two different types of inverters, the Fronius eco is actually quite unique in that sense. All of the other inverters, the primos and simos mainly, have two trackers and a DC boost circuit. However, the eco is a little bit of a different beast, so we thought we'd touch on that firstly. So efficiency wise, if you do actually hit the sweet spot, it can end up being that it will actually be one of the more efficient inverters. It doesn't have a DC boost, as I mentioned, so therefore the DC voltage window is actually going to start off a lot later than a typical inverter that you'd be used to in the industry. And you do have a single tracker, so meaning that there has to be symmetrical strings connected to that same tracker. On the other side of it, the cost saving side of things that we probably touch on a little bit as we go along, that there is actually inbuilt fuse holders, but I'll touch on that a little bit later. So as I mentioned, hitting the sweet spot with the Fronius eco, the DC boost system actually, you can see the scenario here that the SIMO 20 at the top of on the left-hand side and on the top of the inverter has a DC to DC boost. That means it utilizes a step-up capacity to be able to then increase that voltage and start off the voltage window earlier in the piece. The eco, and being an economy sort of inverter, doesn't have this particular component. So therefore, as it states on the right-hand side there, that the narrow input voltage window, which actually starts off at 580 volts. So therefore the sweet spot that we're looking at being able to perfectly hit would be then around about the 690 volt mark on the DC side. so that the inverter is effectively working putting in a lot less effort to be able to then create the required 415 volts on the AC side. Is there anything you wanted to add there, Dimi?
One thing that probably some people it's known in industry as well. It's much easier to convert from higher to lower voltage. There's really two reasons for it. The electronic doesn't work as much. The other one is the voltage drop will typically be less. So in terms of commercial sizing and commercial deployment, it's always the rule of thumb better to have higher operational voltages on the inverter, from the inverter point of view. Sorry. Further on, maybe let's go to next slide.
So in terms of that, it's important to realise that with this singular tracker, as well as then the limitation of the DC voltage window that the Eco presents, we do have a particular recommendation for the Fronius Eco inverter only. It's important to realise that when you're dimensioning these particular systems, that typically there's a lot of different ways to try and work out exactly what your minimum panel temperature is going to be. So there is a recommendation specifically from us that as long as the system is installed in Australia, it's less than 1,000 metres above sea level and the modules aren't on a tracker sort of system, that the minimum temperature can be raised from the -10 that's typically used up to +10 without voiding any of our warranties. So what that's going to mean is that I won't go into specifics today with the solar configurator, and by all means you can get in touch with us if you'd like more information on how the configurator works. But effectively within the module temperature min and max, this is going to then give you options with the sizing of and configuring of the particular strings that would be connected to the Eco a lot more than if you did run with the -10 side of things. Bearing in mind with the inverter ratio, if you're going to use the solar configurator, that we do run between, say, for example, 80 and 130 as the max. We do have a little buffer in there so that if you are setting up a STC sort of system, then you're still within that 133% rule of the CEC.
Thanks, Matty. We'll cover a little bit of communication advantages that are unique to Fronius. One things that the audience may or may not be aware, the actual communication loop that we use, it's called SOLAR.net or SOLAR.net communication loop. Typical for this is that the maximum number of inverters can be up to 100 in daisy chain topology. This basically means that the inverters are chained one from another, so one continuous chain as it's shown in the picture here. So basically we have input and output as being marked out with every inverter. So first inverter out, in and out, and so it goes until we reach the last inverter. Important thing to realize is this is what's called a multi-drop configuration, which means there will be one master and all the rest of the inverters will be technically called as slaves. So the master will actually drive the communication in the back end. Other thing as well with master-slave combination, it's important to dedicate inverter ID or numbers starting from 1 to typically 100. Reason for that is you got to be careful when you do actual commissioning that you don't want to have same IDs because this will cause that specific inverter to lose communication. Bear in mind the first and last inverter on the chain have to have the termination plug-in, which looks like above, which is basically just a short between some internal pins. How that looks like in the actual communication chain we'll actually see now. So basically the plug goes at the beginning of the chain and the last of the chain. This enables the whole SOLARnet loop to be completed properly. If we go to the next slide, we'll go in a little bit more details on what the SOLARnet loop means. Basically all this Fronius Snap inverters are compatible with this communication protocol as described, or SOLAR.net. In the back end, there's actually two communication protocols that are being deployed. One is RS422, that's the communication between the inverters, and RS485, which is basically communication between any smart communication capable devices such as Fronius smart meters and the actual master inverter in this case. What would be interesting to see is that on the right here we have a typical graph which shows maximum distance between typical communication protocol and the actual length of the cable that can be used. Why do we mention this? Is that with our communication protocol, we typically, as we said, we use 422. This is telling us we can go up to around about 1 kilometer in maximum string length, which is quite a bit, and offers quite a few flexible options. In regards to the smart meter communication capability of 485, the baud rate is set up to 9.6 kilobits a second. With the inverters, it's 57.6. Other thing important to mention here as well is the multiple data points per site. What this means is that if you have a big commercial site, you could potentially have several connection points to the online tool that we offer, which is called solar.web. At the bottom, what that means is that as those tools are getting aggregated on the back end, you just need to add those data sources. The actual graph for production and consumption will be shown as one integrated source. Do bear in mind when this is getting deployed, zero export can only be done on the inverters on the same loop. So if this is being deployed, typically it means the site is full export. If we go to the site, so this is the communication capabilities that are typical for Fronius and Eco series specifically. We've looked at some smart deployments and how we can actually deploy these inverters to a specific site, and I'll just leave Matt to continue forward with that.
Thanks, Timmy. So there's two probably main priorities of the way that we work out the sort of location of the inverters. The first one would be a centralized plant whereby all of the fusing and combining of the strings would be done prior to the connection on the DC side to the inverters. And typically the inverters are going to be positioned in, as it says there, a centralized point that's typically right next to where the AC distribution happens. The other option that you're going to have is then a decentralized sort of plant. Typically the inverter is going to be mounted on the back of the panel frames, and a lot of the string fusing would actually take place inside the inverter or right next to the inverter, depending on the situation. And then therefore you'd have actually a longer distance to the AC distributor. In terms of the centralized sort of scenario that we had there before, so meaning that the combining and fusing happens before the inverter, you can actually have DC connector kits. What this will enable you to do is utilize all of the different connections or inputs on the DC side of the inverter. So you could actually then go up to, for example, 25 square mil on one particular option, and then the lower one there, you can actually go up to 35 square mil cable cross section. That would typically be used mainly only for an eco. However, if you did have a point where you wanted to actually then combine strings on a SIMO, that would take place as well. The simple fact would be that you'd have to then disable the second tracker, and it would be all an input from one particular source. In terms of the decentralized sort of things, whereby the inverters would be mounted in the field in all different areas, as we said before, there is only one MPPT. However, you do actually have the ability to be able to then run the strings directly to the inverter. So on that one tracker, we actually have then 6 particular inputs, and each one of those inputs has then on the positive and negative side a fuse potential inside the inverter. So we do actually send the inverters out with a shorting pin originally in there, meaning that if you did actually fuse the strings before the inverter, that these would stay in there. So it's not a case where that the fuses are already installed in the inverter. If you were going to then run the strings directly to the inverter, then you could then run, but depending on which inputs you've used, then install fuses in these particular blocks, which are actually all located in the connection section of the inverter. So just a little bit of an update on the inbuilt DC isolator compliance side of things. It was disputable in the past that any connections that would have above 4 strings, so either 5 or 6 strings connected to a Fronius eco inverter, would or would not require external DC isolators. The good news is with the Amendment 2 happening as it is this week, we will actually be able to then have the potential to use the DC isolator in all different scenarios and configurations with our inverters. With the particular accreditation and certification that's happening with that at the moment, we're in the final stages of having that taken place. So once that's completed, we'll be releasing that to the industry and letting you know. So thought you'd let you know at the moment. So if you do have any commercial sites that you're quoting for at the moment, this may be a cost saving that you can take into account if it's going to be installed in the near future.
Thanks, Matty. I just wanted to check on something before, maybe just highlighted that whenever shorting pins, whenever combination is being used, shorting pins can stay in place. Obviously, when the centralized solution is used with individual strings, then fuses can be used with eco. So in saying that, we've run some scenarios where we believe the flexibility of eco can be highlighted and used. Typically what we've tried to do, as listed here, we've tried to use a small, I'd say a small to medium commercial system compared to using 2 inverters of ours and 1 competitor. This will become obvious in the slide coming next. What I wanted to highlight here is that we've tried to run 2 typical comparisons, A and B. A would typically be a shorter option, if you will, so shorter DC and shorter AC runs. B would be a typical longer one. Probably we need to highlight that as well. We've tried to maintain 2% total voltage drop across all options. Obviously, the AC would be below 2 as well, and combined as 2 as well. Where this is going to become obvious is option B, when some options are going to become above the limit, but we'll see that as we go along. So if we go to the next slide, we've tried to run 2 baseline comparisons, 2 Fronius inverters versus 1 competitor 50 kVA bigger inverter. There will be 5 baseline scenarios we've tried, 3 hours in a way, and then 2 competitors. The reason why there's only 2 competitors there is because we were having troubles locating a 1 inverter of that size that would have centralized and decentralized option. That's why it's only 2 options there. We basically, the 2 scenarios are inverters can be installed on the roof or maybe somewhere on the wall close to the connection point, and obviously centralized and decentralized option for us as well. We've run some scenarios, and in the back end we've arrived to some figures as shown here. We'll see 2 tables, A and B, so that'll be the 2 variations that discussed. One thing that's come up as obviously obvious, but the typical using inverters on the roof and having longer AC runs is not cost effective, typically because when we run DC, we have typical higher voltage, which then allows us to maintain smaller voltage drop with smaller cables. Options 1 through 3 is Fronius based options. We could see that some of the options are more cost beneficial than the others. as can be obvious. What this cost includes is on the DC side, we've tried to include the cabling, the DC isolators, and whatever used, and the DC combiners. On the AC, we only used cabling. Also, this is just running a normal base case scenario, so inverters installed, obviously roof or not. As you know, that the site can be quite different from one another, and which means that cost can be can change quite a bit. Also, this will also depend on the buy price on specific products as well. We've tried to maintain neutral approach in all the scenarios, so same costs, so we can arrive on apple-to-apple based scenario. You're more than welcome to ask further questions on that later on. One important thing with commercial, especially with commercial deployment of Fronius, especially big inverters, ECOs in this case, is the secondary protection requirement and integration. As you may be aware that all the systems in Australia above than 30 kVA rating from the local network, as well as the 400% requirement, will say that there's a central requirement protection that has to be included in the system. Well, that means that there's that typically would be a second disconnection point for the generation equipment. You can see a small graph on the right side here that there's a typical grid protection device or relay that senses what's going on with the grid, with the LV side of things, and then decides to connect or disconnect the inverter generation devices or the inverters. That's typically done through devices such as AC contactors, usually for low currents. If the currents get higher, typically motorized circuit breakers are being deployed. What's important to realize here is that as contactors typically are split in two categories, let's say smaller than 63 amp and higher than 63 amp, they all require enclosures to be installed. It's just, as you may be aware, smaller contactors are much easier to install, commission, and I'd say troubleshoot in a way as well. If we go to the next slide, we'll actually see what we're trying to communicate across here really. We see there's three typical pictures left. If we could start from left and go all the way across, we'll see a small typical 63 amp contactor. Looks like something on the right, and then as we go, as the contactor size rises, that basically we get something bigger in the middle here, and then motorized circuit breaker is basically a breaker with the add-on shown on the picture here. Why this matters and how this is important is that with the ECOs, we have increased flexibility for that disconnection point. Why that matters is that, well, typically if the contactor size is smaller, we do have a small area inside the ECOs that can be potentially used for disconnection. Obviously, it depends on site and size as well. But that is shown in the picture on the far right here. There's a small DIN rail that can be used for that typical 63 amp contactor. Also important thing as well, if as the size is getting bigger, contactors grow and motorized circuit breakers kick in, well then the requirement for the enclosures changes. Typically they require back plates, bigger enclosures, and more labor as bigger cables are being involved as well. And also aggregating the system to one disconnection point reduces the redundancy level of a system. So if a system device fails, it may drop the whole system instead of if you had multiple disconnection points. If we go further, we'll see a typical AC integration. So obviously with the disconnection point comes the AC integration part as well. From experience, typically the AC integration part can be in likes of AC load centers or panel boards, and then AC distribution boards. Load centers are shown at a typical look of a load center is shown on top right. Distribution board, that will be bottom right. Differences obviously size, cost, and capabilities they offer. Prices that we were able to find is typically that the load centers can range anywhere up to $300 more or less, with sizes up to 100 amp. Distribution boards typically off the shelf. You could buy, let's say, 160 amp 36 pole for somewhere around $1,300, and then as the current increases, maybe at 250 amp, it could be found on site for something as as high as 150 plus or minus, obviously. What I wanted to communicate across here is that control boards, distribution board and panel boards, when you buy off the shelf, it's always will be more cost effective. Why that matters is that usually as system sizes grow, there's been a notion of that custom made boards needs to be used on site. Well, that's not always the case. If you do, with our ecos, we do offer the flexible options on where to put the protection, which can enable end customers and clients such as yourself to save further cost in terms of the AC switchgear choice that's being deployed. Obviously, this will be site specific and site dependent, but the option is obviously there. If obviously you have more questions, please feel free to shoot after this. Next, if we go further, just want to touch a little bit more on the smart options we offer and export limitation capabilities that are present there. This is a typical picture of a Fronius smart meter, 50 kA. This has interesting for this meter is that it has two typical current inputs capabilities of 5 amp secondaries and 1 amp. What you've probably met on site will be 5 amp secondaries. We do support what's called a Y measurement topology, so there'll be a typical three-phase, what we see on site. You could also use it for single phase. Be mindful that this meter expect, if used for three-phase, or let's say two-phase, sorry, expects to see a 200-degree shift between the phases, so you can't technically use it with a swirl line or 180-degree split phase systems. And it comes with a class 1 power accuracy, so it's not as accurate as a revenue grade meter, but it's nearly there. If we go further, why is this important? Well, this meter can be deployed in what we call HV metering scenarios. Why and how that can be done? The picture on the bottom right actually shows the typical wiring scenario. This is an extract from the manual. If you look at the picture 3-3E, this shows the typical voltage transformer option that we have. So instead of measuring an LVY topology, you could measure HV site by using VT transformers. What we support here is a VT ratio from 0 to 500 and CT ratio from 0 to almost 10,000. It's important to note that as this is an accurate meter, the burden that we pose in the measurement circuit is very low. It's 0.3 VA. And on the bottom left, we do show a little bit of how the choice of the cable size can impact the burden on site. Be mindful that this will also depend on your CT of choice and the class accuracy it comes with. But the point here is it is very accurate and presents very low burden across to the metering circuit, and obviously not shown here, but it can be used with CTs in series. This is a typical deployment with current measurement output, such as 5 amp CTs. So you could potentially use existing CTs outside, obviously subject to DNSP approvals and customers approvals and so on and so forth. If we continue onward, some typical common issues we've seen with this meter is that the CTs are not installed in the right direction. Rule of thumb, what you need to be cautious of, all CTs come with measurement S1, S2, and P1, P2. P1 always measures source, which is your grid, and if that's the case, then S1 as being configured will be the source on the secondary circuit. As that's being discussed, that needs to be configured in the picture shown here. Also, what I forgot to mention before, I do apologize, this meter comes with RS-45 capable option that we could use to control systems on site. So how this works, the RS-45 is just connected to the plus and minus terminals on the actual data manager on the master inverter, simple as that. Other typical issue that we see here is misaligned CT with voltage reference. For example, the red CT is connected with the blue voltage reference. It's a bit harder to troubleshoot, but we'll give you a bit of tips on how that can be used. There's a link at the bottom here. So how this can be used is if you use this link, bear in mind the IP address needs to be the IP of the Fronius user interface of the master inverter in a way. So if you do that and you use this actual request in your browser, you'll get a response which will look something like this. Basically, if you just have a look through the details here, it's very easy to troubleshoot per phase scenario on how your site looks like. One is what we recommend is turn your solar off and then measure what's the actual power flow per phase, something measured as real power P. If you're seeing a negative value there, that's a telltale sign that CT is wide in reverse. Also, you got to be cautious of the power factor present there per phase as well. If your load typically don't have very low power factors, obviously subject to load, but if you start seeing some numbers there in the likes of 0.1, 0.2, then that's a telltale sign that the voltage reference coming from a different phase. So that can be played around with to get the correct measurement. If we go further, we do have of our second option of a smart meter, which is a 480V UL meter. What's different from this meter with the other meter? It doesn't come with a display, but it does come with an option called voltage input CTs. These are typically more cost-effective option from the 5M CTs, and typically they present a voltage signal, so burden and accuracy is not too big of an issue. Something to be cautious of, because this is a voltage signal, we have to use twisted pair for the CT wiring, otherwise there might be some noise being induced there, some noise issues as well. And it's easier to deploy and use with what's called an integrator or Rogowski coils. As you know, to use a Rogowski coil on a big commercial site, you would need something called, I'm sorry about that, an integrator, which makes it a bit easier to install, especially if you have bigger sets of cables coming and connecting to the site. If we go further, then we'll come to the Fronius PV-Genset, with, in my personal opinion, is a unique Fronius advantage on the market, but I'll leave Matt to touch on this topic a little bit.
I hope you all kept up with that. Okay, so we're jumping to the Fronius PV-Genset. Thanks for all those nuggets of knowledge there, Dimi. So in terms of the PV-Genset side of things, there's two different sorts of scenarios that people generally look at when they're going to determine whether it's going to be a viable option to install solar, where it would be in place of the, for example, a diesel generator. And there's a low penetration sort of scenario whereby that the solar is only taking up let's say, for example, 20 to 30% of the total peak loads. You'd also then have a high penetration sort of genset, whereby the solar is actually a larger percentage of what the peak loads are. So we'd need to have a look at being able to then control and, for example, ramp up and down the inverters so that we keep within the guidelines of the PV genset setup. You can see there on the right-hand side that there are particular savings as to how it all comes together. But let's have a look at all of the componentry firstly. So the way it all is set up, so we've got then firstly the inverter, as you can see there, and hopefully everyone knows already that what the inverter actually does. We've also then got a Fronius PV system controller. Now this is specific for genset sorts of setup, and it's going to measure all of the power flows in the system to be able to then control and make sure that the power is being delivered in an optimal manner. Then you've also then obviously got the genset itself, or the diesel generator. This is going to be the primary source of the power. Typically, we normally want to have the minimum loading on the generator at 30%, but I'll go through that in a minute. The actual loads that you're going to be controlling, so or that you're going to be matching the consumption with, is, you know, typically maybe not an entire factory like on this scenario, but it could be, for example, irrigation pumps, or it could be a lot of different scenarios whereby it's a closed sort of scenario where you only have the diesel generator and the solar within the scenario. You'd also then have the current sensors that are attached to the PV system controller, and that's actually obviously going to then manage or work out exactly which way the electrons are flowing. In terms of the backup feedback contactor, this relay is going to enable the PV system controller to operate not only in isolated grids, but we also would have the potential to later on down the track have a look at potentially batteries and that sort of scenario. So the sorts of rules that you should consider when you actually have a look at the PV-Genset sort of things, or if someone's asked you to potentially quote on this sort of system. As I mentioned before, the normal rule of thumb is that 30% of the minimum genset loading, unless it's stated by the genset manufacturer, as I mentioned, of the total load. So at any point in time, you should always be running the gensets at a minimum of 30%. The sizing, as it says there, the maximum load as well as the maximum generator size should be considered when you're working out the size of the system. So meaning that the original size of the solar system, so it's not a case of actually filling the entire roof or filling the entire field with solar, but it should be considered to match in priority with the generator in question. In terms of the actual DC to AC oversizing of the particular inverters that you're going to have on site, the over dimensioning of this or oversizing of the inverters should be taken into account and tried to be maximized as highly as possible, as well as then taking into account which orientation the panels are going to go in, bearing in mind, for example, in the morning, if you're needing higher loads in the morning, that we're going to orientate a lot of the panels to the east side, and vice versa for the afternoons to the west. In terms of the actual, what we call the PV-Genset easy requirement, that only actually needs one common point of measurement. There is actually also an advanced version of our genset controllers. We won't be touching on them today, but there is a possibility to be able to install them, and we can always go through them with further information later on. In the bottom right-hand corner there, we've also then got a PV-Genset checklist. So this is going to be, let's say, a viability checklist of working out exactly if it's going to make sense, or if the numbers all work out in terms of not only costings, but also the total setup and calculations between the solar and the genset side of things. So in summary, all of the inverters from Fronius will actually work with the PV-Genset systems. If you do a total off-grid genset setup, then we do actually have a MG or microgrid 50 or 60 setup that can be set up on the inverters so that it will function within this off-grid sort of scenario. There's also then extended voltage and frequency limits that we can fully configure. In terms of the compatibility, as I mentioned, the easy side of things is going to be typically for only one generator by itself, whereas there is professional or advanced options using what's called a DIFE controller. That's another manufacturer there.
I just wanted to add on something a little bit. The PV-Genset Easy Controller, in my opinion, it's become even more interesting option as well as because petrol and diesel prices are just increasing as time goes by, and especially those regional customers with irrigation specifically. It can present itself as a unique, easy solution, because if the graph that we saw before, you only need one controller and the inverters in order to make it work. Bear in mind, inverter is a current source, so it does need a voltage reference point in order to function properly, which in this case is being provided by the generator. But if you do think about it in terms of energy flow, and especially with the easiness of deploying this actual solution, it can be a unique solution in going forward, let's say to small to even medium commercial system, where cost saving is the primary driver and simplicity as well. Yeah, that's a bit extra to that.
Awesome. Yeah, no, that's brilliant, Demi. No, I totally agree. And I mean, the gensets haven't been deployed as much in Australia as what we, I suppose, would like to see. But in the rural areas, it's definitely becoming more and more important from what I've been discussing with people. So as it says there, we do have a full tech support area, including the manuals and any smart guides or instructions. They're available through our website. If you're interested in the webinars that we do now, bear in mind, and maybe you've noticed the sort of consistency that we've been doing our webinars with this year. It's the last Thursday of every month, and you can tune in or register with them through the website. We do also Fronius solutions workshops around the country each month, and you can also work out when we're coming to your area through the website. In terms of this actual video, so this will be available on through our YouTube channel, and all of our webinars and any instructional videos will be available through there. So what I might do is open it up to the question and answer sort of time, and let's have a look and see if there's any specific questions that people have asked that we can go through that will affect everyone. Okay, well, everyone must have totally taken on board all of that information, and now they're going to be absolute masters at PV-Genset and any commercial systems. So didn't notice that there was any questions there. Oh, wait, someone's put their hand up. Okay, someone's got a question, but they haven't officially asked it yet. So I think they might be typing.
So what do we do if there's a generator on site? I guess a little bit more specifics would be appreciated. Is that a grid connected scenario with an off-grid generator option, or hold on? There's more questions coming in. Hold on a second, sorry.
Maybe just answer the question that you began.
Okay, let's start. This is from Michael. What do you do if there's a generator on site? That's, as I said, it depends on the actual scenario and situation as well. Typically, 4777 requires disconnection of a generator, any inverter-based equipment if the generator kicks in. Obviously, because the generator doesn't really like external generation and possibility of export inside the generator. We are working on some potential solutions for that. At the moment, the actual official rule is from the NSPC as well, you have to disconnect your generators when the grid disconnects, unless there's a third-party controller that can control the overall power flow. Hopefully this answers that question. Okay. When will the DC isolator change happen? That's another one.
So yeah, that's in the process, as I mentioned. We're in the final stages at the moment. So there's been some final paperwork required by the certifier to be able to then put that through. So as I mentioned within the webinar, we'll be releasing that information to the industry once it's all done and dusted and the I's are dotted and the T's are crossed.
There's another one. How do you switch the inverter off as per the rules? I imagine this is with the generator. Typically, this we do have a white paper how to sync inverters with generator, but you could also do that via the if it's a biggest commercial site, via the contactor control. So the main protection relay could potentially sense and disconnect the actual inverters, or probably one way forward would be, if there's an ATA switch on site, sense the actual setting or the connection point from the switch, and then decide if it's to the grid, then turn the inverters on. If not, then turn the inverters off. This is the secondary protection, obviously. Okay.
So it looks like there's a lot of different range of different questions that, and we've, I suppose, sparked quite a lot of different random interest from everyone within the webinar. What we might do is answer those questions individually as we go. And for more information, you can always contact us directly. That's in the application engineer team. That would be either through PV-Solutions-Australia@Fronius.com, or if you do have our direct contact details, you can always get in touch with myself and Demi or our Sevi and Rod in our team to be able to assist you with those things.
Okay.
So thanks very much for your time, everyone, and we'll be in touch with everyone that's asked a question, and yeah, look forward to seeing you at the next webinar.
Thanks again. Hopefully you enjoyed it. Any questions, feel free to ask us over, send us an email, and then we'll respond by the end of the week. We'll try for sure.
Thanks very much, guys.